Today we will talk about time-dependent circuits, and we will talk about RC and RL circuits. For problem 1, we will have a capacitor that was charged with charge Q0. So charge on the plates of the capacitor at time t0 is Q0. And I put this capacitor with capacitance C that is given in a circuit. This is the switch, and then I have a resistor with a given resistance R. We neglect self-inductance, so self-inductance is 0. I put L0. What we are looking for? We are looking for the charge on the plates of the capacitor as a function of time. So at time moment 0, I close the switch. We have current in this circuit because the capacitor is discharging, and we want to know how Q depends on time. First of all, the law. Which law we will be used to solve the problem? Faraday's law, that tells us that integral E dot dr over closed path is equal to minus d dt integral B dot ds, where integral B dot ds is the flux of the magnetic field through the surface S bounded by this path, and ds is the area vector. I need to follow the steps that we always follow when we work with circuits. First of all, let's choose the direction, let's choose the charges on the plates of the capacitor. I will put plus Q here and minus Q here. If I have positively charged on the upper plate of the capacitor, when I close the switch, the current will be flowing in this direction. This upper plate will be discharging. So natural choice of direction of current will be clockwise. Then, what's next? Now I need to choose the direction in which I go around the loop. We always go in counterclockwise direction because we follow the convention and we follow the notations in your textbook. So I go in counterclockwise direction. You use your right hand, you bend your fingers, and your thumb shows the direction of ds, that is out. And this shows the direction of dr. So we go around the loop in the counterclockwise direction. Now let's look at the right hand side of this equation. I have d phi dt, but there is no external magnetic field. Self-induced magnetic field, we neglected. It was given neglect self-inductance. So flux of the magnetic field is 0. The right hand side of this equation is 0. What is the left hand side of this equation? Let's go around the loop and we follow our usual rules. So what is E dot dr with our choices when we go across the capacitor? dr is down, the electric field is down, which means that E dot dr is positive. I put plus Q over C. Then we keep going around the loop. Here dr is up, current is down, which means that current density is down, and electric field, which is rho J, is down. dr is anti-parallel with the electric field. E dot dr is negative. I put minus. And the magnitude of E dot dr across the resistor is IR. We close the loop. Nothing else is here, so we put it equal to 0, since the right hand side of Faraday's law is 0 in our case. Okay, do we like this equation? No, we don't, because we have two unknowns, one equation and two unknowns. We don't know Q and we don't know current. So we need to relate current and the charge on the plates of the capacitor. current by definition is plus minus dq dt. Let's find out, what do we choose, plus or minus? With our notations, with our choices, the current, this current, is leaving positively charged plate of the capacitor, which makes the derivative dq dt negative. So this q decreases since current is leaving positively charged plate. Since the derivative is derivative dq dt is negative, we choose minus. When current is flowing towards the positively charged plate of the capacitor, then we choose plus. In our case, the current is leaving positively charged plate, minus. Now we bring this in our equation. What do I have? I have 1 over CQ minus R. Current is minus dq dt, minus and minus plus R dq dt, and this is equal to 0. Now we have one equation and one unknown variable, Q. So let me rewrite this equation. I will rewrite it this way. R dq dt plus 1 over C Q, and this is equal to 0. I can even divide by R, both sides of this equation. Then I will have dq dt plus 1 over RC Q, and this is equal to 0. Look at this equation. This is first order, linear, homogeneous differential equation that describes Q, the charge on the plate of the capacitor, as a function of time. Now we need to solve this equation. If you know already how to solve this equation, you use the method that you like most. I will use the same method as the textbook uses, which means that I will guess the solution of this equation as alpha, unknown constant, times exponential function to minus beta t, where beta is also unknown constant. Why am I doing this? Because I see that the derivative of some function plus the function itself is equal to 0. So this is a reasonable choice, since derivative of exponential function is exponential function itself. So now I need to find alpha and beta. First, we will find beta. Find beta. To find beta, I take my guess and I bring it into my equation. So this Q goes into this equation, which means I need to figure out what is dq dt. dq dt is alpha e to minus beta t. And now I use chain rule, which gives me minus beta. That was dq dt plus 1 over RC, 1 over RC, Q, which is alpha e to minus beta t, and this is equal to 0. What we will do next? Let's simplify it. I divide both sides by alpha. I divide both sides by e to minus beta t. And what we have here is minus beta plus 1 over RC is equal to 0, which brings us to beta as 1 over RC. We found beta. Now we need to find alpha, and I will use different color to find alpha. Find alpha. To find alpha, we need to use the initial conditions. We will use the initial conditions. For initial condition, we have charge at time moment 0 is equal to Q naught. So after we found beta, our solution looks like alpha e to minus t over RC. And if I use my initial condition, I will get Q at time moment 0 is equal to alpha e to 0, time moment 0, e to 0 is 1. So it is just alpha. And at the same time, we were given the charge at time moment 0 is q naught. So we found alpha, that is q naught. Now we know both alpha and beta. And our solution, q as a function of time, is equal to q naught times exponential function minus t time over RC. We solve the problem. Let's find the current now. What is current? Current is minus dq dt. So I need to differentiate this equation, this formula. Current as a function of time with our choices is minus dq dt. I keep minus, then I differentiate this, it will bring me to q naught. It will bring me to minus 1 over RC when I use the chain rule, and derivative of the exponential function is exponential function itself. Minus minus plus, so current behaves as q naught over RC times e to minus t over RC. Let me put this equal sign right here. Now let's plot q as a function of time and current as a function of time. So my graph for q as a function of time, q as a function of time, will start at time moment 0. Time moment 0, e to 0 is 1. So we start at q naught, right here, q naught. And then, as time goes to infinity, 1 over infinity is 0. So as expected, there is exponential decay. The capacitor is discharging. So with time, charge on this plate of the capacitor will be 0. And when time is equal to RC, which we call constant for RC circuit, when time is equal to RC, I have here q naught divided by exponential function, which is 2.7. So at time equal to RC, my charge decreases by a factor of 3. So where is RC? It will be approximately right here. Right here is RC. Am I right, or I did it too much? Probably too much. Let's put it right here, RC. And now what I'll do next, I will plot current as a function of time. So what will be current as a function of time? Let's look at current. Before I start my clock, current was 0. And now at time moment 0, t0, e to 0 is 1. At time moment 0, all of a sudden, current jumps to q naught over RC. Why does this happen? Because we neglected self-inductance. That's why we have this sharp jump of current. And then, again, I have exponential decay. As time tends to infinity, as time t tends to infinity, then 1 over infinity is 0, and I have 0 current. And we understand what's going on. When we wait for a long time, steady state will be established. And then current through the capacitor in steady state is 0. That we know really well from our previous chapters when we worked with steady state situations. So we found the charge as a function of time, and we found current as a function of time for this problem.